and that's constant. Take the derivative, get 0. So that's pretty awful, right? But you can write it down, and we get something that's reasonable. So I lost something, didn't I? Shit, you guys. I lost a term somewhere. Oh my God, I made a mistake. Hey, everybody. Oh, that's right. I'm forgetting my common filter. I made a big mistake. It's funny. This is a conditional mean. I need the conditional distribution of S. Oh my God. I made a boo-boo. That's so funny. Hold on a second. Yeah. Oh, shit. Oh, fuck. I screwed up right there. Oh, sorry everybody, let's stop. So this is almost okay. We should have been suspicious when we lost y. So I've got God, my notes are messed up too. Hold on a second. Wow. So yeah, this is a what time is it? Yeah, 4:23. So, somebody help me out here. So we definitely know, we have our common filter experience to know that given y, we know the conditional expectation distribution of S given y. It's Gaussian, and we can work out its the conditional mean and variance. What's puzzling me right now is why am I ignoring n? Because S and n both appear in here. I'm going to plug in big S and big N here, and it's true that n is always n0 sigma squared, but once I observe the sum, the conditional distribution of each changes. And my so. So if you work out our formulas, we're taking the conditional expectation, assuming that S has this variance theta old. And the mean turns out to be a scaling. So I'm not going to work this out now. We've done this. Well, I'm troubled. Okay, hold on a second. Just bear with me, everybody, okay? Sorry for the goof. I don't know what's, yeah. Anyway, so that's something you can go back and look at your notes when we're doing common filters and innovations and all that. You can work out the conditional distribution of a signal given observation of signal plus noise. Okay, so I'll take that out. But what was troubling me is the fact that Q theta has not just a conditional expectation of S, but N. However, let's jump ahead. No. Okay, no. In the EM algorithm, we take a conditional expectation given y equals y, and we assume the model is the last theta parameter. So it's a conditional probability, but our model is theta old. We're taking the expectation with respect to that. But rather than take this expectation and then try to take a bunch of conditional expectations, it makes more sense to first take the gradient so we can kill off any term that doesn't involve theta. All right? So basically what I'm going to end up doing is I'm going to take I have the expectation of this whole monster, and I take the derivative with respect to theta, and it appears in these two places. So I'm going to end up with the again, I substitute capital S here, I substitute capital N here, I take this conditional expectation, and this appears, the 2 pi I can ignore, the log of the product is the sum of the logs, so I'll get a minus 1/2 1 over theta. Okay, so I've taken the derivative inside the expectation. Here I get, just as before, I get a plus 1/2 1 over theta squared. And then I get my damned S squared, which was giving me trouble. And then the rest of it, like I said before, disappears, so I can ignore it. And then conditioned on y equals y and theta old. Phew. All right, so I was worried about myself. Why didn't I work out the conditional distribution of n? And the reason is because there's no theta sitting in front of it, so it disappears. All right, and so then you get it. I claim that given this model and given this observation, I know what the second moment is. It's the variance plus the mean squared. So I've got the variance, which is this baby here. But again, this is a second moment, so I got to take the variance and I got to take that baby squared. All right, so these are 0 when theta is theta nu. That's the definition of theta nu. And assuming that there's a, solving for this, we get theta nu. And there you have it. So and it turns into, if you unravel this whole monster, here's what you get. All right, so that's actually the recursion. Basically, theta k was my old, and theta k plus 1 is my new. And does this converge? I claimed it does, and yes, it does. So it turns out that provided you initialize it with, if theta 0 is positive, which isn't obvious, so this converges, right? I mean, it's a horrible nonlinear function of theta, so you have to do a lot of work to prove this converges. But it's worthwhile seeing this, that it's non-trivial, that, why on earth did we get lucky here? Why is it that theta does converge, number one? So as you let this run, theta k will converge to a limit, and why does it actually converge to the right thing, the ML estimator, right? What time is it? Yeah, 4:30. Well, I'm not going to do anything fancy. Let me just give you 2 lines of the main ingredient in analysis, all right? Unless there's a question. I know I made a meal of this one. Yeah, Neil. I just don't want to, oh wait, this business? Yeah, I'd have to go back to like February, or March. It's basically, if we go through our tricks, look at the best. We know that the conditional expectation. We know the best estimator is the conditional distribution is Gaussian and all of that. No, it's just it's another calculation I don't want to do. Yeah. But the fact that the conditional variance doesn't depend on the observations. And this is linear in the observations is a common filter fact. It's more linear estimation. But let me just show you one beautiful fact, which is the key to analysis. All right, so this is just a minute. So So all right, you don't have to do this factorization. It's for analysis. So you can always write a density or a probability mass function in two variables. In this case, x was the pair yz, I said. Is the density for y times the conditional density of x given y. You know? You could just always factor like that. This is Bayes' rule. In fact, this is just defined to be this divided by this. Okay, so that's the definition. And then you go through and you look at this Q theta business, and you play around with it. I guess I have to write it down again. Oh yeah. Okay, we've got that. So I use the factorization, which I can always do, and the log of a product is the sum of the logs. And this thing here doesn't depend on anything. And then you have the log of this, this funky thing here. All right, so you all know that I'm in love with relative entropy. So what I'm going to do is I'm going to stick in some relative entropy here. I'm going to get another colored pen. So I'm going to divide by this kernel, this conditional distribution with the old guy, and of course that's doing damage. So I've got log of 1 over, so I've got to add on this to redo things. Wow. Yep. All right, so what have I done here is I've said that Q of theta, the thing that I have to maximize, is exactly the thing you maximize for maximum likelihood estimation, plus the relative entropy. This doesn't make any difference. So what I mean is maximizing over theta Q of theta is the same as maximizing over theta, the ML thing, and then plus, well, look, there's an expectation. Let's see, it's backwards, isn't it? I'm dividing instead of multiplying. So it's minus the relative entropy. I've got to maximize. This is minus the relative entropy between K with theta old and this other guy here. All right, because this is supposed to be on top, so to flip it around, I have to put the minus sign. And of course, it's a conditional relative entropy. I can put D conditional if you want, because it's a conditional entropy given y equals y, but that's okay. So basically, EM, and see what we're doing is we're trying to make our new guy close to the old guy, right? This is a penalty from deviating from your old guess. So this can be viewed as a standard regularization trick. So it's so EM is ML plus with regularization. And relative entropy is a standard trick to try to put a penalty on deviation from your old guess, right? This is a penalty, right? I mean, if this distribution is very far from this, you'll get a huge penalty. There's a minus sign there. You'll have a big negative component, so you're not going to do it. So this basically is what's going on. So this, of course, this was not the motivation for EM, but this came out later on. And I'll bring this up again next lecture because that's how you prove convergence. So basically, based on the fact that maximizing this is the same as maximizing this, you get a proof that this guy is always converging, which is really, really awesome. Or at least, well, part of a proof. All right. All right, so that's it. Is that clear? Any questions? I know you have questions, yes, all right. Neil, you're the troublemaker. Yeah.
The relative entropy is not symmetric, and you have to be careful how you formulate it. What's your intuition there? How do you know that theta pole should be on the top?
Oh, no, it's just a definition, that's all.
Or because you could also...
Oh, no, that's the definition. No, the relative entropy between P and Q, or Q and P is how we always had it. Big definition there. The way I remember this is that Q given P, I think of it like division. So I know I'm going to have a 1 over P there. But if this is just our friend, that's all. It just comes up everywhere. Relative entropy pops up everywhere. So that's just the definition. And yeah. And so here I'm taking an expectation, and I'm supposed to have, if there's a Q there, I'm supposed to have a Q on top. That's not on the top. And that's why I have to have a minus sign to flip this around. Yeah. Yeah, this just means I'm taking the expectation of this. I'm assuming X is distributed according to the distribution with theta old. So that means that, this is reality. X is, its conditional distribution is precisely given by that. Yeah. So this is just exactly relative entropy, with y given, so that, let's forget y is fixed, so we have a new probability space where everything's conditioned on y equals y. So it's just flat out relative entropy with that new probability space.
In the E step, you said we can generate x's according to a Markov chain, right?
Mm-hmm.
Now, in this maximization step, can we also use a Markov chain to calculate this expectation?
No,
Or the relative entropy part bit?
No, this is just analysis. That's why I underlined analysis. This has nothing to do with computation. You'd never use this.
Can we use it?
Well, you'd have to go through and factor this and stuff. This might make things even more complicated. No, this is not used anywhere. Yeah, and this is all the E step. There's no maximization here.
It's all maximization.
No, I'm saying that, it's true. I'm saying maximizing Q is the same as maximizing this. But I don't see how this is no easier than, this is not a computational discussion. It's analysis. This representation doesn't help with computation. This is the first step in proving convergence. The 2 points here is that when we maximize Q theta, we're maximizing the objective function we really care about, but with a penalty term from deviating from our previous guy. That's it. All right.
Okay, so you
Yeah.
view that as a penalty.
That's one way to think about it. This is a positive term which gets used if k theta is very far from k old. So it's something to keep you close to where you were before. That's
Like
all.
a stopping condition.
Nah, it's not a stopping condition. It's a penalty. All I can say. It's a penalty. Yeah, there's no stopping condition. It's a penalty. It's just what it is, okay? So, I mean, yeah. And we'll see next lecture that it's really useful in getting insight in how this thing evolves. All right? And it's also useful that this is really a really standard trick is to, when you're constructing recursive algorithms, you take the thing you care about and you put in some penalty from deviation from your last guess. It's just absolutely, you go to NIPS and every other talk will have this regularization term, and often with relative entropy. It's really, really standard. But again, this is for analysis. You wouldn't use this in computation. All right, that's it. So there's no lecture on Thursday. I'll send out an announcement. A bunch of us are going to be in DC, and and that's okay because we have time. So we meet again next Tuesday to finish this up. Yeah.
Probably if you don't look at